So today I'll be talking about palette and compositional diffusion, which is going to be constituted by two papers. Uh, palette is an image-to-image translation model using diffusion models. And the second paper is going to be a compositional visual generation, which uses compositional text-based generation model. Uh, yep. And the outline is going to be, first I'm going to be talking about the palette. So I would like to first introduce you to who might not know about the task itself of translation, image-to-image translation. So it was first introduced by one of this paper, image-to-image translation with conditional adversarial networks, and this paper, pix-to-pix, when it's given an input of some kind of like a drawing, just a line, then the pix-to-pix is going to give an output of a cat that is colored, or maybe other image translation tasks, such as on the right side, it's going to generate a full image that changes the whole color and structure. And inspired by this project, they also perform various different tasks for this paper, on this paper. So in terms of inpainting, GANs are normally used for inpainting, but however, GANs often requires auxiliary objects, and so that is why they want to repropose this inpainting method. And also in terms of image uncropping, they show that that we are going to show that conditional diffusion model trained on these large data sets can uncrop across image domains. And we're also going to focus on colorization, which is going to be coloring the image, and JPEG restoration, which is a task of getting rid of the compression artifacts, and the multi-trust training, which is actually, they are saying that multi-trust training has not been done well in the previous projects, and this is the first time they are proposing this. So their model will constitute by one model that can perform all these four tasks, including inpainting, image uncropping, colorization, and JPEG restoration. So I would say the method itself is very simple. As we all learned about the conditional diffusion models, this framework also follows a similar thing. So this, as you can see, the method is basically formed like this. It is in a slightly different form from this above equation, but actually it is doing the same thing, where this gamma here is the same as the current noise level, where we observe a lot in denoising diffusion models, which is normally introduced as alpha. And the condition is the input, which is going to be the x, where we normally see it as like texts, which is given as input together with the input that we are trying to generate. And also, in terms of architecture, the model architecture is based on unit architecture, which is basically what most of the introduced diffusion papers were doing.
So sorry, what is y in this case?
Y will be the y. As you can see on this one, this is actually normally this is considered as the input x. So x is going to be given as an input, and the for process is going to give the.
So y in this case is like the noise or the intermediate step.
Yes. So the term is just different, but actually the equation itself is exactly the same.
And x is what we condition now?
Yes, x is what we condition on.
And gamma is the noise level?
Yes.
Okay.
So to look at the evaluation metrics, they propose that since they are proposing various different tasks, including like inpainting and such as colorization and many others. They are proposing a unified evaluation protocol. So last time, Chang introduced some of the evaluation protocols that are being used in GANs, which included FID, which is efficient inception distance, but they also include various different scores, such as inception score and classification accuracy, which they only use top one, and perceptual distance. This is going to be Euclidean distance. In their paper, they were using it as Euclidean distance in this inception V1 feature space. And they also use the sample diversity for measuring the novelty. And they also use human evaluation and full rate, and which is full rate means like if people can figure out if this image generated is by human or AI. So I will move on to experiments on this paper because I would say that in terms of method, there weren't really many things proposed. So in terms of colorization, you can see that when a grayscale input is given, there is an output that is colorized, and this is the reference image where you can just check if this image is actually similar to the original image they were trying to put in. So you can see that most of the images are colorized very well, as this, and in their experiment, they transform an input grayscale input image to a plausible color image, as I've shown in the previous slide. And one of the things that they did different from the previous papers is that they maintained the RGB color space for the generality across tasks, where other papers that were proposed use something as LIB color space, which allows like to quantify the color using like the independent color space. But for this paper, they are saying that diffusion model actually can just use RGB color space without independent color space, using an independent color space. And also they show that they achieve state-of-the-art results. As you can see, they are using various different metrics that they proposed. And you can see that in terms of most of these scales, all of these scales actually, they perform much better than other given the prior works. So yeah. And the next one would be in-painting. So in-painting job would be, as I said before, when a user inputs something like this on this grayscale, then the part would be erased, or it's going to be filled with different kind of objects. So let's say for this gray part, as the user colors this gray, then this part in this green rope will be gone. And also in terms of in-painting, they've also achieved a state-of-the-art results. And one of the points that they wanted to make was that when using palette to maintain their generality, they were passing this binary in-painting mask, which is normally what they do in the previous works. But they are filling the masked region with standard Gaussian noise instead, which is one of the good points that you can use from diffusion model generation. And the next part would be uncropping. Uncropping is a task that the user can slide up, and then the AI would give the colored part. And the reference image, when you look at the reference image, you can actually see that this part was generated as a blue sky. And on this one, they created well on like they created well robust nature. And especially in this experiment, I was quite impressed by the experimental results, but in terms of the robustness. So when you actually look at this picture, the original given picture was just including this part, but when you slide into right side or left side, the model can actually robustly generate all the other parts, like including this part. And I would say this is quite an improvement, quite an impressive experimental result. And this is also impressive because most of the papers that were presented beforehand of this paper were extending input images along only one side of the given border. But this paper focuses on along all sides of the given border. And I would say this is one of the biggest differences given by this paper. And they also perform JPEG restorations, which is when you see on this left side of image, you can see that the image is actually in very low resolution, and they can output a high resolution image. And in terms of experiment, what they did differently from the previous papers is that normally all the papers were considering input images that have quality factors are over 10, but this paper will perform even better results when they are given quality factors of 5, which is going to be a high compression rate on the input image. Yes.
Sorry, so can you explain a little bit more about this JPEG restorations task? Because for the previous one, like uncropping, I can understand that they crop a part, they try to generate that part, and they condition on the other parts that's not cropped, right? That's how they do conditional generation. For this one, what do they condition on? Like you have this, so it's from, if I understand it correctly, it's from low resolution to high resolution, right?
Yes, low resolution to high resolution.
Then what? So what do they condition on? And or in another way, like if I'm giving this low resolution image and I try to do super resolution.
Yes.
So where should I start? I also start with a bunch of noise, and then what?
Can you please rephrase the question? I don't think I understood well.
Yeah, so let's say we have this image on the left, right?
Yes.
And then I try to go to the image on the in the middle.
Yes.
Right? That's my input and output.
Yes.
So using the diffusion model, what I can do is that I can just try to generate the middle image from noise, right? That's what a regular diffusion model will do.
Yes.
Right now, so seems like we are saying we're doing conditional generation.
Yes.
Then how do we condition on this input image? Like, how do we use the information provided by this input image?
The input image would be given as the X, which was shown on the equation before, I think. If that's what you're asking.
So you just, so basically it's like you get this embedding,
yes,
and you just concatenate it together with your noise.
It's not like concatenation, I would say,
Okay.
though, because it's a function that has 3 variables, which is input and
okay.
yeah.
I see. Then your function has 2 inputs, right?
Yes.
One is, then let, okay. Then in that case, how do I know I am doing like super resolution rather than, let's say uncropping? Why I make this image super like higher resolution rather than generate some other stuff, say other trace to the left of it or to the right of it? Like in the previous example, the robustness example you just showed, right? That long picture. I also give it a crop, as the middle part.
Yes.
And then the model try to generate the left part and the right part.
Yes.
Here, I again give it a picture, but the
Yes.
model didn't generate other parts, but make this picture higher resolution.
Yes.
So seems like there are two different things going on, right? So why do we have these two different situations? How did we tell the model what to do for each of these two cases?
First of all, thank you for pointing that out. I've actually didn't thought about that point, but why I didn't think about that point was that actually in most of in the paper, they don't describe any difference in terms of method when they do JPEG restoration and uncropping and other kind of tasks. So basically the only method that they provided was the equation that was given in the first part. And for the rest of the experiments, there is no other, they say, there was no other implication of change of the equation or something like that. So.
Okay. Did they, do you know that, did they use the same model for two tasks? I remember there was a multitask setting.
Yes, they are using the same model.
They use the same model, okay.
Yes.
Then, yeah, if it's the same model, then there must be some difference between these two, right?
Yes.
Otherwise, how should the model know whether it should do super resolution or do uncropping? There, okay. But yeah, but we can continue now. I can check the paper.
I will check on the question, and I'll update on the email for everyone to know. Sorry for confusion. Yeah, so I would say that in terms of like the remarks, the paper, for me, it felt like the paper didn't provide any theoretical novelties, because the paper was giving exactly like the same conditional diffusion model, which uses the input, just change the input of text to an image. And the paper proposes new metrics that can be used for further line of research. And I would say that is one of the contributions of this paper. And also the paper proposed like a multitask model that can be used for high quality results, which is also quite impressive. So I'll move on to compositional visual generation, which has more of the, I would say, equation part of theoretical part of contribution. So for like the overview, the paper is proposing to combine this energy-based model, which is another line of research that from the diffusion model, and combine these two and create a compositional visual generation. And I would say from the previous presentation given by Shichang, there was one of the models that were named GLIDE, and they are specifically targeting the problem that was given by the GLIDE, which is that when the sentence is given as in a wrong, even if the sentence constitutes a lot of different conditions, and then the model will generate weird images. But in terms of this model, you can see that even though the sentence is very long, they can actually recognize these and kind of texts and use these different composed texts as this condition for this generation model. So
can you please stay in the problem a little bit longer? Just to try to understand, for example, object 1 and 0.1, 0.5, what does that mean?
Is that the coordinates?
Coordinates?
Yes.
Oh, so
so they will give the coordinates and just I don't know, there weren't any discussion about the objects, but I think they put in something like a small green box on 0.1, 0.5, and large green box on 0.5, 0.3, and the generated picture will going to be composed like this.
Okay, then because this one seems to me is like very challenging in the sense that we provided the logic and the generated picture has to follow those logic or constraints, which is different from the previous generation task, because as long as the picture is beautiful, right? So nobody really thinks about from constraints perspective. So just try to understand the setting here. For example, when we say object obj1, as human, we know it's object one, but like what does that mean? It could mean anything, right? Because why they kind of associate this object one to this green small box? Because without any context, it's just a.
Yes, that was why I said it might the object one, object two is something like a green box and small green box, large green box. But I think for this image, and there is a huge image that is going to be presented by this paper, but most of the images they are showing is just using object one, object two. So I think they are just compressing that long image description into just object one, object two, just for simplification.
Are those objects predefined? Like we have an object dictionary. Or it can be, for example, you mentioned that, oh, this object one is like green box, but at least here we didn't see that, right? So where do we have that information? Is like in the dictionary?
When you look at this image, this is actually what they do. So large metal cube, small yellow metal sphere, large metal cube. So it's going to be mostly names, I would say. But I think in this part, they were using a specific data set for this specific task that is named by object one, object two, object three. So it is not that this model is going to be understanding each object as a green box if it's given as object one. But as you can see here, it's going to be the model needs input as metal object or something like a green box, some kind of description just for the model to actually provide these images. So I would say the description using object one, object two is just a abbreviation of the sentence that they given.
So then, assuming that you are a user, right? So you're going to give the text-based description instead of object one, object two. Is that right? Okay.
Yeah.
So can we go back to figure 4 again? Yeah, so here I see some of the images don't have object one, object two, this kind of labels on it. So for example, the first column, right, lace. In this case, the ones with this object one, object two, object three, are those just for illustration, or it's like the generative model can actually put text on the image?
Oh, it's just a
for
description, yes.
But why some of the images don't have this object one, object two?
I think it is for like, because the compositional diffusion itself is just a enhancement that includes like these and kind of compositional like more enhanced information. They want to show that for even though they have like various different objects, ours can actually provide a well-sequenced model. So when you look at EVM, even though this one actually creates 5 different objects, is the position itself is different from their given model. And when you look at the coordinates, then it'll what they're saying is that when you look at the coordinates and when you look at the conditions, when different conditions merge, their model performs better.
But in other words, like even for this hours model,
yeah,
all this object 1, 2, 3 are like manually labeled. So once you get the generated image, it's just the 5 objects there. And then you look at the input prompt and you look at the image. You manually label each of them as object 1, 2, 3. Is that correct?
So when you actually use this model, it would be something like a human woman on the left side and right men on the right side, like that, rather than just using information such as object 1, object 2. So it's going to be, let's say, human 1, let's say, well, Einstein on position 0.1 and 0.2, and well, some other guy, Jobs on 0.3 and 0.4. This is going to be the input.
Okay.
Yes, and this is an example just for that this composable diffusion can actually comprehend these different joint distributions rather than just to show if these positions are actually working, I would say.
I think just, this is just my opinion. I think just
yes.
compare these 4 different models. The most obvious thing to me is that it can correctly capture there should be 5 states. The other models either has less than 5 or more than 5.
Yes.
But yeah, because this object 1, 2, 3 are like a post hoc, like just for illustration. I guess that part can be a bit confusing about what the model can actually do. Yeah. Anyway, I think I get it.
Oh, okay.
We can move on.
Okay, I'll move on. So the natural question that can rise from this proposed way of combining energy-based model and diffusion model is that why we should combine these two, especially why we should bring in the energy-based model as concept when we want to perform this compositional generation. So first, to introduce to give a slight introduction to this energy-based model for, actually I was very new to this concept. I didn't really look into these energy-based model before looking into this paper. So I was also quite new to this concept. So I would like to share some of my insights reading through just understanding EVMs. So energy function uses this term as the target maximizing data likelihood. So when you look at energy. So when you look at this term, this is going to be E minus X, and this is going to be the normalizing factor actually. And why they use energy function in the first place is that if people want to model a data distribution, we normally assume something as a Gaussian distribution or some other distribution such as like Bernoulli distribution or something like that. But energy functions can actually provide a description to any kind of form of the data distribution, and that is why energy function has the most information inside this function, and it can actually show the whole data distribution that is possible. And however, trying to train based on this energy function based distribution is a very hard task because zeta is unable for the model to train. And therefore they want to use a sampling technique, which is normally for the paper that they are using for this energy-based model, using a derivation method that will divide this term, which is the target of the maximum of what they want to maximize, into these two terms of gradients. And this dividing these two was just like a theorem in terms of which is included in the Langevin dynamics. And after dividing this gradient into two, they can again tweak this equation into another form. And why they actually have to tweak this form is that explicitly sampling from this distribution itself is impossible, and they want to move on to another distribution that is highly similar to the original data distribution. And for this new data distribution, when the k goes to infinity and the lambda goes to 1. Well, actually, when lambda goes to 0, then the Langevin dynamics equation, this Langevin dynamics equation on whole itself would be same as the energy function, which is introduced by this paper. And that is why many of the recent papers on EVMs were using this kind of stochastic optimization technique, which is a sampling technique. And I would say this equation itself was just a EVM motivated equation, and this compositional diffusion paper also uses this equation for further generalization of this diffusion equations to EVM models. And also, to move on to why they actually use this EVM model, is that EVM models can produce these different kind of equations very easily. So conjunction and disjunction and negation was proposed by this paper, compositional visual generation with energy-based models. And you can see on this Venn diagram more easily that when you have a male and wavy hair, there is going to be some parts that are conjuncted, and some parts like this, all male wavy hair and smiling are conjuncted. Then it's going to be have three different conditions. But when it's just a male and it's not wavy hair and it's not smiling, then it's going to be minus instead of plus. And this kind of energy-based model uses this energy-based equations can derive these conjunctions, disjunction, and negations very easily. So for further explanation, there's this concept of conjunction, which they provide in this paper, compositional visual generation with energy-based models. And these equations are going to be used on this compositional diffusion paper, same as this paper. So as p theta, the data distribution is proportional to the energy, they are using this kind of equation. When they have C1 to Ci conditions, if they want the data distribution produced to have all these conditions to be AND, then they will simply just multiply these probabilities, and this is going to be presented as this, because it is a mathematically, yes. And also for the concept of negation, which is very similar to the last one, is going to be presented as this. And for this one, I would say it is fairly easy to just understand. The part of this one is, the point of this is this alpha, which they use as a regularizer term. And if alpha is actually going to be smaller, then this term will be smaller, and then the condition 1 would be weaker, and then they will yes. So then they will ignore this condition and go to just C2, just provide an output image that is just conditioned by C2. And So they use this same method same method for the derivation of negation method and conjunction method on this paper too. So for example, this is the model workflow for this concept of conjunction, and when you input an image, this is going to be composed by several different sentences. So they are, if they give more and more explanations, then they can create more and more highly accurate images, which was not the case in normal diffusion-based models, because when diffusion-based models receive too much information and too many conjunctions or too many negations, then it's going to provide a more it's not going to understand the sentence well. And this is the part where the conjunction occurs. And so basically the diffusion part is based on the denoising diffusion probabilistic models, which was introduced several times before. And you can see that they use the exact same equation as denoising diffusion probabilistic models. And what they are trying to do is combine this equation with the equation that is given by the EVMs. So they are going to interpret diffusion models as EVMs and EVMs as diffusion models. So when you look at these two equations, you can easily see that the only difference in term is that this part and this part. So this part, this is normally what we call what we want to optimize in terms of diffusion models. And when you look at the energy-based model, actually in this term itself is proportional to the score function that we always see at denoising diffusion probabilistic models. And that is why, because these two are proportional, we can actually see this as when we try to optimize this equation, then we are also optimizing this equation. And because the remaining parts are the same, when we are optimizing this equation, then we are also optimizing this equation. So we don't have, so without further derivation, they just can easily move between diffusion models and energy-based models in terms of equations. And to show a little bit specifically how they perform this is that so for example, when they compose this EVM, as usual, what normal EVM does is going to have different kind of and independent EVMs, and they are simply going to conjunct these composed EVMs, and this is going to provide an easy explanation for these all different conditions. And to input this equation is highly effective for just using as a diffusion equation, because as I've shown in this part, these two, what is?
Just turn it
Oh,
on.
my iPad doesn't show any. Oh, this is yours. Okay. So, yes. Basically, all of the following equations are going to be the process of changing these diffusion-based equations into EVM-based equations. And for example, sorry if there's a lot of confusion. I will try to answer if anyone asks questions. So
I just want to make a comment. I think the idea to turn this logical conjunction negation into the algebraic operation on the energy function is very smart, right? So, and also intuitively it's quite correct, because if you think about the probability of two events and you want to do the conjunction, so it's corresponding to the multiplication. And since energy function is kind of in the log form, so that's why it's just a summation. Yeah, for this part, it completely makes sense. For negation, I think it's worth of further discussing here. So why negation can be just considered as the ratio of the two. For example, we have the two probabilities, and it's say negation is just the first probability divided by the second probability.
This part, yes.
Suppose we don't have C2, we just have C1, negation of C1. So on the top, it's going to be 1, is that right? It's just inverse of the probability. Yeah, so I think here the main bridge is like how we can connect the conjunction and negation into operations different on probabilities. So if a conjunction, then they say, oh, it's just the multiplication of the two probabilities. If it's negation, I guess it says it is equivalent to 1 minus, 1 divided by the probability.
Yes.
Okay.
So I think in terms of negation, I think they have, as they say like this, negation must be defined with respect to another concept to be useful. I think this is just a way for them to create a proportional equation that can lead to this kind of equation so that they can easily optimize later on.
Yeah, so this one is less natural. So there are lots of tricks to play. For example, this alpha to control the scale, and then you do have this proportion, meaning that the result does not have to be in the range of 0 and 1, and so it has some problems. So that's why they need to have this additional trick.
Yes.
But at least the trend is right. Negation, like orange are probably smaller. If we take the inverse, then the negation probably is going to be bigger, right? So roughly it's right. Just technically, it needs some special treatment.
Yes. So to move on to the actual negation part, this is going to be actually. So after the intuition based on diffusion equations and EVMs, you can see that this part xt this equation can be easily turned into this kind of equation, and this p compose is going to be changed to like this, and where the e term is going to be changed into this term, this whole term over here is going to be changed into this term. And right now, I would say that this equation in whole looks intuitively correct, but I do not know like the derivation or exact derivation in terms of these how these equations are interconnected. But and this part was the conjunction related part, and this actually this slide was very quickly made, so it doesn't have any description. But yeah, if anyone wants to talk more about this conjunction part, then I would welcome any talk. and this part is the negative negative composition, and this part will be the these two conjunctions are the only thing that they are considering for this paper, and they don't consider such as like these different parts. So, but the original EVM papers are actually considering all these different kind of equation, all these different kind of conjunction methods in terms of equations. But I would say they didn't provide anything else than these two. And yes, actually, this is going to be the last slide of my today's presentation. I would be happy to provide some more information on the slide that I will create further on. Sorry for everything that I had been a little bit less prepared. I was very busy this week doing several different jobs. Yes. Any questions? Okay. That's going to be the end of my presentation. Thank you.
Thank you.